In this video, I set out the contents of parts 1 to 5 of this series of videos. These contents were originally included in part 1, along with what is now the abstract video. Now that I've separated these out, part 1 has just 2 sections. The first section explains, in 6 slides, the scientific motivation for the program of research which became covariant compactification. In the second section, I move on to the key high-level concepts of the theory, which are necessary to introduce at the beginning if you're to understand the contents of parts 2 to 5. These weave together into a conceptual structure for the theory. In the second video in this series, we'll start at the absolute foundation for this body of theory, with the concept of a diffeomorphism on a manifold. This video will focus on the tangent fields to diffeomorphic flows and their covariant derivatives. We'll look at how these relate to isometries and conformal maps, and to the manifold factorizing as a product. This, we will see, brings in gauge fields. We'll find equations for these tangent fields for when the flow trajectories are and are not geodesics. We'll discuss geometric solutions to the equation for geodesic, especially in 10 dimensions. In the third video, we'll move on to considering fermions. We'll group the states in the first generation of fermions into a 32-component spinor and describe how its components can arise as harmonics on the classical vacuum manifold. We'll take a particularly detailed look at the spinor components on the spatial 3-sphere, which corresponds to a specific moment in cosmic time. We'll see how rotations on this 3-sphere induce transformations on the harmonics under chiral SU2 cross SU2. For the 6th sphere of the classical vacuum manifold, we'll see how rotations induce an SU4 mixing of the spinor components, and how our model sits in a loophole in O'Rafferty's no-go theorem. This video closes by looking at symmetry breaking, including how the SU4 and chiral SU2 cross SU2 symmetries are non-linearly realized, but within these, the SU3 cross SU2 cross U1 invariance group of the right-handed neutrino, precisely the gauge group of the standard model, remains linearly realized. In the fourth video, we turn to look at field dynamics, studying this in a flat space limit. We focus on eigenfunctions of the translation operator, their wave numbers, and their energy momentum. We then show that local changes of phase act like a force, changing their wave number and momentum. This is quantified by a gauge potential, as happens with inertial forces and in the Aharonov-Bohm effect. For superpositions of these waves, we find uncertainty relations for these quantities. This is all done without explicitly quantizing the fields. In the last video, we applied the principles of the previous one to the case of product spacetimes. For the de Sitter factor space, they guide us towards both Einstein's field equation and Heisenberg's uncertainty principle, while for the compact factor space of extra dimensions, they guide us towards Wilson loops for the strong force. I also provide a derivation of the Dirac equation within the context of this model. I then run through some priority areas for further research. In particular, a more precise description of how the SU4 gauge symmetry is broken to SU3, the meaning of electroweak symmetry and how the Higgs field arises, how the indeterminacy of quantum mechanical measurements arises, and questions around fermion masses. Finally, I provide a closing summary of the 5 videos, contrasting covariant compactification with other Kaluza-Klein theories and providing links for my key papers and other outputs and resources on my work.